Hello and welcome to this Design Practice 2 Module 35. Just prior to this, you have watched about two different modules which are corresponding to the FDM process, that is the fusion deposition modeling process, where you found out how you can actually take care of the zones which are the support and the zones which are the parent materials. Let us get into a slightly different gear today on rapid tooling. I think I had just introduced this area in the last lecture, but we will just elaborate on it a little more and try to finish up. So, rapid tooling broadly describes any mold making process that can create tools quickly and with minimum direct labor. So, basically when we are talking about, let us say, so when we are making a tool, for example using injection molding, for injection molding dies for example, or where there is a pressure die casting and we need to make a die. So, it basically gives a very quick way of arriving at the shape, overall shape and size of an engineering component which would later on go into a product. So, it is a very rapid manufacturing technique where it is merely that you fill something with a liquid which gets solidified and it makes the overall shape, size, etc. So, this is somehow classified as a rapid tooling, and if I want to develop such a rapid tool, there are many additive and subtractive manufacturing processes which need to apply, and then also you have to integrate the data management process that comes out of, let us say, a CNC system or a computer system in a logical manner, so that a very complex profile, topology, etc. can be created. Now, this is like creating some kind of a die or a mold and using it many times so that you can make many engineering components at extreme rapidity. So, it definitely uses rapid prototyping techniques, can all be applied to a variety of applications from, let us say, injection molding, casting, even sheet metal stamping operations using a die which has been manufactured falls under the category of rapid tooling, the science of rapid tooling. Okay. And so, basically if I looked at what are the different kind of tools which are generated, we will have indirect tooling and direct tooling, and I think we had just begun to illustrate this area. So, indirect tooling is basically something which incorporates pattern based methods by casting a tool using rapid prototyping or other processes that depicts the part to be molded. Examples are, for example, sand casting and investment casting. So, in sand casting what is going to happen is a wooden pattern, okay, and this pattern is used again and again for getting the sand into place inside a flask, where this pattern can later be occupied by molten metal and a part comes out of it. Okay. So, this is actually an indirect tooling. So, although there exists a pattern, but this pattern will not be used directly, okay, in place while you are actually injecting the material or making the material to go inside, and therefore it is merely a shaping tool which is utilized before something is created which can be used for the tooling purpose of the overall shape of a cast that would come out. Okay. So, this is indirect tooling, it is not directly participating. There is also a direct tooling. It is probably a method where the mold, inserts and other components are made directly by a rapid prototyping machine. Example, let us say the 3D printing to create a die of metal powders followed by sintering and infiltration to complete the die following by CNC machine is something that is a direct tooling that you are creating which will participate, okay, in the process. For example, in pressure die casting, whatever is a mold is a direct tooling. So, now you have to create this tool. So, the tool is basically the one which occupies space and creates a space for liquid metal to later on fill at a high pressure and generate an overall shape or size which is that of an engineering component. So, you are using directly the mold for doing this kind of a casting process. Now, when we look at, for example, investment casting, again there is a lost wax method. So, you basically have a outer created by wax which would be later on filled and the wax will be disposed of. So, then again something which is used to pattern that wax around, etc., where the cavities could be created can be considered as an indirect tooling. So, there are these classifications of one which directly participates, another which helps in creating that cavity or that shape which would later be filled up by liquid, okay, in order to make the engineering part. So, this is how the classification is. So, there can be soft and hard tooling as well. So, for example, it can be used, the soft tooling can be used to make multiple wax or plastic parts using conventional injection molding processes. It produces short term production patterns. Injected wax patterns can be used to produce castings. Okay. So, soft tools can usually be fabricated at the rate of 10 times faster than a machine tool, and they are usually polymeric in composition and basically made up of soft materials. Now, when we look at the materials of tooling, so it can be very many. For example, there can be wax patterns which are used to do indirect casting applications. There can be also polymeric or plastic parts. So these are all in the soft category of soft materials. Similarly, there can be hard material based. For example, steel or aluminum is shaped into a certain die or a certain shape where the desired component is produced using essentially CNC machining or some other precision process, and then this metal participates in, for example, pressure die casting, etc. So there the boundaries are metals, okay, there the boundaries are hard components. So therefore tooling can be either soft, made up of polymer, wax and other alternate materials, or hard based on the steel and aluminum and other different kind of metals. If I looked at the indirect rapid tooling techniques, there are many folds. For example, you can have spray metal tooling, you could have silicon rubber tooling, you could have the 3D cal tool, the vacuum casting processes, okay, and then the epoxy tooling. So these are some of the indirect rapid tooling techniques. And when we look at silicon rubber tooling, for example, it is a soft tooling technique, it is an indirect rapid tooling method. So the process would necessitate the making of a rubber mold with a master pattern, of course, which is usually made on a rapid prototyping machine, and then we finish the pattern and the desired appearance is basically shaped up on the particular rubber pattern. And you can do different castings, like for example this silicone rubber or RTV, which we also know as PDMS, okay, can be used or can be casted. So it is a soft tooling technique which is also an indirect rapid tooling method. So basically it comprises of the following steps. So you basically make a master pattern usually on a rapid prototyping machine and finish the pattern to the desired appearance, and then casting of the silicone rubber, or let us say what we better know as PDMS, polydimethyl siloxane, around the pattern to form the mold, and then inject the mold with 2-part thermoset material to create molded plastic part. This is represented here. So in the first instance the RP pattern is being made using some either FDM or other processes that I have explained in the last lecture. Then you basically cast around this material, which is a silicone rubber, forms a very good matrix, okay. In MEMS also we have seen this is all some kind of a very high aspect ratio replication or micro casting material. Now once the negative of this pattern is created, let us say you have a air tube and filter and all those things inserted, so that whatever goes in does not create any bubble or anything. We must be able to open or cut this into half so that we can retrieve the pattern off. So the pattern is retrieved here, and this is now a mold cavity where there is again a air vent and a pouring riser runner combination, which is being shown here. So once the material is poured, and this material could be urethane or other plastic, which can actually use this soft polymeric mold as a filler, and so therefore this plastic can go inside and fill the space while all the air can get oozed out from the air vents, thus creating this kind of a part. It can be solidified and this can be gotten rid of later, and many cycles can be made through such soft molds or soft parts. So this is what the silicone rubber tooling technique is like. Similarly, so these are some of the illustrations of what can be done. So with silicone rubber you can see this complex part being created through a plastic material, where the plastic can be retrieved later and the mold can be used for the next run, okay. Then so obviously the silicone rubber tooling provides a fast and inexpensive process through a mold, which can result in excellent part cosmetics, options of using multiple materials, etc., and the same tooling is there. And so it's really a very flexible process of soft tooling. The process is also suitable for small and medium sized plastic parts particularly, which are abundantly utilized in many applications. Another benefit of the silicone rubber tooling is the negative draft undercuts that can be achieved due to the flexibility of the mold materials. So you don't really want to go much on the draft side, actually make negative drafts happen, because obviously the mold will expand a little bit because of its own soft nature and be able to accommodate the parts, and we want to make sure the parts are as much aligned to the dimensions as possible, okay. So this aspect has to be put in all the different tool making or indirect tooling making approaches for this rapid prototyping or this particular process, this rapid tooling process. So then there can be epoxy tooling. So this is another way of, just like we made a silicone rubber tool, we can make a epoxy tool. They used to manufacture prototype parts or limited runs of the production parts. So here the epoxy tools are used as molds for prototyping of injection molded plastics. It can be used as molds for casting. It can be used as compression molds or reaction injection molds. The basic process is illustrated here. So you have the fabrication of molds begin with the construction of a simple frame around the parting line of an RP model. So there is a frame which has been made here, you can see around the parting line, and there are exactly two halves, one is the upper half and the lower half, which is about this parting line, and you have sprue gates and runners which can be added or cut later once the mold is finished. The exposed surface of the model is coated with a release agent, and epoxy is poured over the particular model. This is the RP based mold which is used to carry the epoxy. The epoxy would go and fill the cavity, okay, and generally aluminum powder is also sometimes added to the epoxy resin, and copper cooling lines can also be placed at this stage to increase the thermal conductivity of the mold. Once this pouring happens, it dries up and creates again a aluminum filled epoxy. So in a way the epoxy tooling method is used to make reinforcements, okay, which would be getting rid of some of the problems associated with the silicone rubber mold which you saw in the earlier step. So basically once the silicone rubber mold is made and a polyurethane part is made out of it, that part can be again utilized in order to build a epoxy mold around it, okay. So the epoxy, and particularly the metal epoxy composite, is able to ensure that you have a high strength mold which lasts longer, is able to be multiply used, etc. And so there whatever polyurethane part is coming out can be used as some kind of a core, in order to basically make the mold completely in epoxy. This is showing that kind of a run. So with a certain core which is in place, which you are not able to see in this figure, and with a lot of these other copper lines, etc., which are for easy cooling, the epoxy mold is being developed, okay. So this is developed along a parting line, meaning thereby that the patterns are split patterns, with one half being done through one half of the polyurethane part which comes out. So basically the other half is also simultaneously processed, and so therefore that's how a mold would realize. The advantages that this epoxy tools would have are that, number one, that it is made up of slightly harder material, so it lasts longer in comparison to what you saw in the silicone mold or the rubber mold. However, they have limitations. So you have a limited tool life, again poor thermal transfer, and sometimes you have to intentionally make cooling lines happen because epoxy itself is a thermally insulating material. You also have a tolerance dependency on the master pattern. So basically if the urethane pattern that you are formulating from the previous run has a certain surface issue or a surface tolerance issue, it may need to be machined in order to serve as a core print for this, or a core for this particular new epoxy pattern that you will be building. And obviously aluminum filled epoxy has low tensile strength, so that way the overall mechanical properties of the mold is also severely compromised if we talk about epoxy tools. Now there are other techniques to make molds stronger. You had already seen how the initial step silicon rubber tool was made. One of them is thermal arc spray. So basically here you can make a mold stronger by putting on the pattern the pattern can be made out of an RP model, but you could essentially have metallized vapor being coated on the top of this pattern. So typically these metallized vapors are coated by creating two metal electrodes in an arc and then blowing gas at a certain, or inert gas at a certain velocity through it, so that it can carry whatever the metal, whatever metal droppings or whatever metal melt has been formulated in that arc region, and can quickly atomize because of high velocity. So now the atomized form of that metal, liquid metal which is being formulated at a small rate can be considered to be like a metal mist, and this mist is actually coated on the top of the pattern, so that it can, when the pattern is extracted, it can comprise of metallized surfaces of the mold, which can later be thermally cured, etc., so that there is sintering between the material, and then that can result in some longevity of the particular mold that is in question. Okay. So here the whole concept is about creating a high hardness shell material to an otherwise RP pattern, and then backfill the remainder of the two shells with inexpensive low strength low temperature materials on tooling channels. It can definitely provide a hard and durable face, okay, of the pattern using this wire arcs process. The spray pattern is either controlled manually or automatically by robot control. These are some of the parts which are being again sprayed through metal arc processes. Okay, current wire arc technologies are limited to low temperature materials, however, as such materials are available in filament forms, which makes the spray coating easier over patterns. Another soft tooling approach is the 3D Kel tool process, which is based on a powder metal. It's used to make injection mold insert and other durable tooling from master patterns, very similar to spray metal tooling. Only thing is, in this case again the heat sintering approach is utilized to make the patterns harder. It was originally developed in 1976 by 3M and was sold and further developed by the Kel Tool Incorporated. It was named as 3D Kel tool later on. So here what is happening is that you can see in the first step you are fabricating the master pattern through core and cavity and producing an RTV silicone rubber mold out of the pattern. Okay, so this is the RTV silicone rubber mold. Filling the silicone mold with metal mixtures to produce green parts. Okay, so green parts are powder metals held together by polymer binders. So these are some metal polymer matrices, just like you did epoxy aluminum matrix. So that is a metal polymer matrix. So in similar manner there are a variety of other metal mixtures which are there. So you duplicate the silicon rubber mold with metal mixtures, produce green parts, and then the metal mixture is powdered with steel, carbon, tungsten carbide and other hard materials, even polymer binders with particles around the size of 5 nanometers, and then fire the green parts. Okay, so you try to sinter whatever is in the material together, so that there is some kind of a metal polymer matrix. Some of the polymer of course will be evaporated because of the high temperature. So you have infiltrating of the sintered parts which are about 70% dense, and and 30% void space. So this is like more like a hollow pattern kind of, there's more like a hollow material kind of a thing, or where the polymer part or the polymer binder may be evaporated in some case, just sintering together or putting in place together the metal powder which is around. So this is this acts like a pattern, okay, which can be an indirect tool which is utilized in many of these cavities. So what we have learned is that through various surface hardening techniques, for example wire spraying and sintering, or even epoxy aluminum composites, or even some kind of polymer hard materials like tungsten carbide composites, etc., firing them to a temperature where the polymer goes away and there is sintering, local sintering between the metal, etc. The objective that we are developing here is to produce an indirect tool. Now this tool goes and makes a cavity through a material which would otherwise be used for injection molding or some other means without directly participating into the process. So this is how the indirect indirect tooling business would be. There are many direct tooling techniques also. For example, this very famous direct access injection molding, we also know it better as AIM, okay, or laminate tooling molds, or pro metals or copper polyimide molds. Let's look at some of these approaches. Particularly I would be more interested to describe this direct access injection mold. So in this particular process called the direct access injection mold, it refers to accurate clear epoxy solid. This ACES term comes from solids made up of epoxy. Stereolithography or SLA processes are used to produce the epoxy inserts for injection molds for thermoplastic parts, because the temperature resistance of the curable epoxy resins available at present is up to about 200 degrees Celsius, and thermoplastics are injected at temperatures as high as 300 degrees Celsius. So accordingly specific rules apply to the production of this type of projected tools. So in the AIM process, the mold is typically, this is a mold in the AIM process, okay, it's grown using stereolithographic approach. You know how stereolithography works with a part by part building. I had explained this quite clearly when we talked about the rapid prototyping part. So a mold is similar to a regular SLA part, but is the negative image of the particular part to be built and is cut into two halves. So you have split pattern orientation, okay, as you can see in this particular case, and there can be a lot of intricacies defined within the pattern. The negative of the intricacies are defined within the pattern because of the high accuracy approach of the stereolithography process itself, okay. So the cavity can be filled with a variety of materials, of course. So this is the direct tooling, okay. So now you are building with SLA a tool which can be infused with thermoplastics, aluminum field epoxy, ceramics, low temperature metal components. All these things can be extracted directly from the mold. So you have a direct cavity being made by a SLA technique. So this is how some of the direct tooling approaches could be. There are many advantages and disadvantages of this. So advantages are that it is probably suitable for slightly longer, about 100 parts. Both resistance to erosion and thermal conductivity are questionable in particularly the AIM process, but you can increase this by deposition of a 25 micron layer of copper on the mold surface and then sintering it just by using one of the techniques as you used in the indirect tooling case before. There are many disadvantages. One of them is the number of parts that can be obtained using this process is very dependent on the shape and size of the molded parts. If they are too intricate, then this 100 part estimate may not really work out well. It may break the mold just before that. You can also have, if you look at the operator concern or the skill level concern of people, this is a slightly more difficult process, okay, than indirect methods, because you are making the tooling itself, and therefore there may be an aspect of machining, there may be an aspect of changing something on the overall die cavity that is propping up through the SLA process, and there is a very important role being played by skill of operators who are making such tools for manufacture. So this is one of the direct tooling examples. The other is quick cast process. So one of the variants of this AIM is or SLA based process is this quick cast process. So it's a process that allows creation of direct shell investment casting using quick cast lithography patterns, stereolithography patterns. So here the idea is that the SLA part being completely solid, with this quick cast approach you can eliminate 95% of the internal mass of the part. Something like this, you can see all these different quick cast molds being manufactured, okay, by making some kind of a mesh pattern kind of a thing which is still able to be used as a insert for mold making, etc. So with this I would like to complete this section on rapid tooling, okay. So in the next particular module we will start in next week another interesting area of mechatronics and intelligent products. So what I plan to do is probably to give you a introductory 25 minutes or 30 minutes lecture on that, followed by some lab level demonstrations for about 2 hours when we can talk about things like data acquisition, etc. At the lab level, so that you can understand more of applied mechatronics, okay, with some theoretical formulation in mind. With that I would like to end this particular module. Thank you very much.